Welcome to the LearnTech Podcast. If you're getting ready for the CompTIA A Core 1 exam, the 220-1101, then you are at exactly the right place. Understanding PC hardware isn't just theory you have to memorize. It's really the fundamental language of IT. It is the absolute bedrock of your career.
That's the critical point, really. Our goal here isn't just to help you, spit back definitions for the text. We want you to get a real comprehensive understanding of how all these parts, the motherboard, the CPU, the storage, how they all talk to each other.
Because that's what a good technician does.
Exactly. This block of knowledge is a huge part of the exam blueprint. And being able to look at a system, assess what's compatible, and spot a bottleneck. That's what makes you a truly capable technician.
So today we're basically giving you a very targeted, efficient route to mastering this stuff. We're going to sort of build a computer just by talking about it, starting with the main platform, the motherboard, and then moving on to the brain, the memory, storage, and all the little connections that tie it all together.
And we're going to zero in on the specific numbers, the sizes, the compatibility things that the exam writers really love to test you on.
Okay, so let's start at the beginning. We have to begin with the motherboard. It's the literal foundation.
It really is. It's the nervous system, the skeleton, the power grid, all of that on one circuit board. When we talk about its role, it's really two main things: distributing power and organizing the flow of data.
It's the master organizer.
That's a great way to put it. It provides the physical home for every other component, make sure they all get the right amount of electricity, and gives them the high-speed roads to talk to each other. But maybe the most important decision you make with a motherboard, and this is something technicians sometimes forget when they're troubleshooting, is that you are predetermining compatibility.
You're locking yourself in from the start.
You're locking in the CPU socket type, which then locks in the generation of RAM you can use. It is the #1 architectural constraint of any PC build.
And of course, these machines have to actually fit into cases, into the real world. So the most obvious difference is just size, the form factor. For the A+ exam, you absolutely have to know these sizes and, maybe more importantly, what you gain or lose with each one.
Right. Let's start with the big one, the industry standard. ATX, that's Advanced Technology Extended. It measures 305 by 244 millimeters. And because it's so big, ATX is the undisputed champion of expansion.
Maximum of everything.
Pretty much. You get the most space for adding stuff. We're talking multiple full-length PCIe by 16 slots.
Sort of like multiple graphics cards or specialized hardware.
Exactly. For complex rendering rigs, scientific computing, that kind of thing. And you also get the maximum number of RAM slots, usually 4, sometimes even 8. If you're building a beast of a workstation, ATX is where you start.
Okay, so if ATX is the full orchestra, what's the next step down?
That would be micro ATX or mATX. It's the intermediate size, usually up to 224 by 244 millimeters. It's designed to be a balance, a balance between having some expansion slots and not taking up a ton of space.
So you still get some room to add things.
Oh, yeah. You still get a decent selection of slots, maybe 2 or 3 PCIe slots, and usually 4 RAM slots. For most people, that's more than enough.
Okay, so what is the key piece of information a technician needs to know about mATX compatibility?
The exam-relevant nugget here is its backward compatibility. Meaning, because a micro ATX board is smaller than a full ATX board, you can fit a mATX board into any PC case that was designed for a full ATX board.
Ah, okay. That gives you a lot of flexibility for repairs or upgrades.
A ton of flexibility.
But there's a catch there, right? Something that might show the difference between a good technician and a, less efficient one. If I put a tiny mATX board into a giant ATX case, what's the problem?
Well, you've hit on a great point about optimization. Technically, will it work?
Yes.
Yes, perfectly. But you're sacrificing the efficiency of the build. You lose out on the maximum expansion the big case was designed for, and you didn't get the space-saving benefit of the smaller board.
So you just end up with a big, half-empty box.
A big, heavy case with a lot of wasted space inside. And that can sometimes even mess with the airflow, because the case wasn't designed for that specific layout. A good technician thinks about what fits, but also what makes the most architectural sense.
And for the absolute smallest builds, the tiny PCs.
That brings us to Mini-ITX. This is the most compact desktop form factor, a perfect square at 170 by 170 millimeters. It's the go-to for things like home theater PCs or those ultra-compact, small form factor systems.
The trade-off has to be expansion then.
Minimal expansion. You are almost always limited to a single PCIe by 16 slot.
So you get one shot.
One shot. You can build incredibly powerful little machines with Mini-ITX, but you have to be absolutely sure you won't need to add any other cards later on. And cooling. Cooling becomes a huge challenge in that tight space.
Okay, so once we've picked our platform, our motherboard, we need to install the brain, the CPU, the central processing unit. We all kind of know it executes instructions, but what's that actual process, that fetch, decode, execute cycle?
It's just an incredibly fast loop. Fetch is the CPU grabbing the next instruction from memory. Decode is figuring out what that instruction means. Is it a math problem? A data move? And execute is, well, doing the thing. The whole of computing is just that three-step cycle, repeated billions of times a second.
Let's go inside that engine room then. The component everyone's heard of is the ALU.
Right, the arithmetic logic unit. The ALU is the calculator. It's the part of the CPU that does the pure math, all the addition, subtraction, multiplication, and also all the logical comparisons. Is this value greater than that one, A and D, or not?
So anytime you're running a spreadsheet or a game, the ALU is what's actually crunching the numbers.
It's where the real work happens.
Okay, but what makes sure the ALU isn't just sitting around waiting for numbers to crunch? That brings us to the memory management unit, right?
This is a really critical concept. The CPU is ridiculously fast. System RAM, by comparison, is kind of slow.
It's a bottleneck.
A huge bottleneck. If the CPU had to wait for RAM every single time it needed a piece of data, your computer would feel like it was stuck in mud. So the memory management unit, the MMU, steps in. It's the traffic cop. It manages the CPU's entire conversation with the main system memory.
But if the MMU is just managing that slow RAM, what's the secret ingredient that makes it all feel fast?
That would be the integrated cache.
L1, L2, L3 cache.
Exactly. The MMU oversees this cache, which is a tiny, incredibly fast pool of memory built right onto the CPU itself. The cache acts like a high-speed buffer. It predicts what data the CPU is going to need next and holds it right there, ready to go.
So it's all about reducing those slow trips out to the main RAM.
Drastically reducing them. Having that data ready in L1 or L2 cache is the difference between instant response and noticeable lag.
So how much of a problem is this, really? In a modern system, how much time is a CPU just waiting?
That's a great question. In high-performance computing, it can be upwards of 30% of the CPU's time just waiting for memory access, even with all the fancy caching. The MMU tries to fight this with sophisticated prefetching algorithms. It tries to guess what the ALU will need next and pulls it into the cache before the request is even made. Without the MMU and that cache system, the raw speed of the ALU would be almost useless.
That brings us right back to the motherboard, specifically the socket, LGA versus PGA. This is one of those non-negotiable compatibility things.
Absolutely. The socket is the physical and electrical handshake between the CPU and the board. Technicians have to know the difference. LGA, land grid array, is what Intel mostly uses. With LGA, the delicate little pins are on the motherboard socket. The CPU itself is flat on the bottom, which is contact pads.
Okay, so the risk of bending pins is on the motherboard side.
Right, and the alternative is PGA, pin grid array. That's traditionally AMD's territory. With PGA, the pins are on the bottom of the CPU chip itself. Those pins then slot into little holes in the motherboard socket.
So either way, the main takeaway is that the specific socket-like LGA 1700 for Intel or AM5 for AMD, that number is what dictates your CPU choice.
It dictates everything. You can't mix and match. The pin count, the layout, the electrical signals, they all have to be a perfect match. That one choice defines your entire upgrade path for that PC.
Let's move from the CPU to its best friend, RAM. Random access memory. The system's short-term memory. We're in the middle of a huge transition right now with DDR5, and the specs here are absolutely essential for the A+ exam.
The move to DDR5 SDRAM is probably the biggest memory architecture shift we've seen in a decade. It was designed from the ground up for two things, efficiency and raw throughput.
And for technicians, the first thing to note is the voltage change.
Right. DDR5 runs at a lower nominal voltage, just 1.1 volts. That's a small change, but it adds up to less power consumption and less heat across the whole system. But the headline feature, the big news, is the bandwidth.
And how big is that increase? What are the numbers we need to know?
Well, the bandwidth has basically doubled. DDR5 speeds start around 4 gigatransfers per second, or GTs, and they scale up to 8.8 GTs on standard modules.
In terms of throughput, what does that translate to?
You're looking at a range of about 32 to over 70 gigabytes per second of bandwidth. It's a massive jump. And the capacity is just as wild. The maximum capacity for a single stick of RAM jumped from 64 gigs to a potential 512 gigs.
512 on one stick.
It opens up huge possibilities for servers and high-end workstations.
So what's the technical trick that lets it scale that high?
Part of it is a new feature called Decision Feedback Equalization, or DFE. Basically, at these insane frequencies, the electrical signals start to get messy. DFE helps to clean up those signals, which allows the bus speeds to go much, much higher than they could with DDR4.
Okay, now here's the really important part for a technician to understand, the part that goes beyond just reading a spec sheet, the latency caveat. If the bandwidth doubled, shouldn't all my apps run twice as fast?
That's the logical assumption, but no, not necessarily. And this is the kind of nuance the exam loves to test. While the frequency is much higher, the actual memory latency, the time it takes to respond to a request, is also a bit higher.
Can that be?
It's due to the internal architecture. So when you do the math, the real-world response time often ends up being very similar to good DDR4, usually around 14 nanoseconds.
Okay, so give me a real-world example. When does that massive bandwidth really matter, and when does low latency win out?
Great question. If you're doing something that moves huge, continuous chunks of data like editing 4K video, running big data analysis, or hosting virtual machines, the huge bandwidth of DDR5 is a game changer.
The system is just inhaling and exhaling massive streams of information.
Exactly. That 70 gigabits throughput makes a direct, noticeable difference. But for tasks that depend on instant, snappy responses to the CPU, like competitive online gaming where milliseconds count, or maybe high-frequency stock trading latency is king.
I see.
In those cases, a super high-frequency DDR5 kit with a high latency value might perform exactly the same as a really well-tuned DDR4 kit. The technician needs to know that raw speed doesn't always equal better performance for every single task.
All right, moving from data speed to electrical power. The power supply unit, or PSU, this is the unsung hero, right? It takes the AC power from your wall and turns it into the stable DC power all your components need.
Absolutely. And the single most important concept for PSU, both for real-world efficiency and for the exam, is its efficiency rating.
The 80 PLUS certification.
That's the one. PSU efficiency is just a measure of how much power it draws from the wall actually gets delivered to your parts versus how much is wasted as heat.
And waste is bad. Waste is heat and a higher electric bill.
Waste is heat, and heat is the enemy. To get that first basic 80 PLUS certification, a PSU has to be more than 80% efficient at 3 specific load levels, 20%, 50%, and 100% load.
And now we have all those different tiers: bronze, silver, gold, platinum, titanium. What's the practical difference for a technician?
Each level just demands higher and higher efficiency. A bronze unit might only need to be 82% efficient at 50% load, while a platinum unit has to be 92% efficient.
So less waste, less heat, and a lower power bill over time.
Exactly, which contributes to the whole system lasting longer and being more stable.
Now, the top tier, titanium, has a unique requirement, doesn't it? Something candidates need to remember specifically.
It does, and it's a key detail. Titanium is the only level that adds a fourth measurement point at a very low 10% load.
Why is that 10% so important?
Because most office desktops or home PCs spend a huge amount of their time just idling. They're sitting there, not doing much, operating in that 10 to 20% load range. A titanium PSU's ability to stay highly efficient even when it's barely working makes it way better for saving energy in a system that's on all the time but not always under heavy load.
So when a technician is advising a client, especially a business buying a fleet of computers, that 80 PLUS sticker isn't just a sticker, it's a huge part of the total cost of ownership.
Precisely. A gold or platinum PSU costs more upfront. But over 5 years, the energy savings and reduced component stress from less heat can often make it the cheaper option in the long run. It's a classic short-term versus long-term cost calculation.
Okay, let's talk about long-term data storage. The classic choice. Hard disk drive, HDD, versus solid-state drive, SSD.
And it's still a relevant choice, especially for things like mass archiving. The core difference is mechanical versus electronic.
The HDD is the mechanical one.
Right. It's a sensitive piece of machinery. You have spinning magnetic platters and a little read-write head on an arm that has to physically move across the platter to find the data. Its speed is physically limited by how fast those platters can spin, usually 5,400 or 7,200 RPM.
And the SSD just threw all of that out.
Completely. An SSD is purely electronic. It uses non-volatile NAND flash memory chips. No moving parts means no noise, less power use, much better durability, and crucially, instant data access.
Let's put some numbers on that speed gap, because it's usually the answer when someone complains their PC is slow.
Gap is enormous. A traditional HDD might give you sequential transfer rates of, say, 30 to 150 megabits per second. A basic SATA SSD starts at over 500.
But the real difference is in the access time.
That's the real kicker. Because the HDD head has to physically seek out the data, its random access speed is terrible, somewhere in the 0.1 to 1.7 ms range. You feel that delay. And SSD's access is electronic, so it's in the 50 to 250 ms range. That's the difference between your OS booting in 10 seconds versus a minute and a half.
Now, we know HDDs can fail if you drop them, but SSDs aren't immortal either. The memory cells can only be written to so many times. How do they manage that problem?
You're right, they have a finite number of write cycles. To get around this, SSDs use some very clever firmware tricks. The most important one is called wear leveling.
Wear leveling.
Think of it like a traffic controller for data. The firmware keeps a map. When your operating system asks to write data to a certain spot, the wear leveling algorithm deliberately sends it to a physical memory block that's been used the least.
So it spreads the work out evenly.
It ensures all the memory blocks wear out at the same rate, which dramatically extends the life of the drive.
And what about the other technique, trimming?
Trimming is about cleanup. When you delete a file on an HDD, the space is just marked as available. On an SSD, when you delete a file, the OS sends a trim command to the drive. This tells the drive controller, hey, the data in this block is no longer needed. So during idle time, the drive can proactively clean that block out, making future writes much faster and more efficient. It avoids a lot of unnecessary rewriting.
So with all that, when would a technician ever recommend an old-school HDD anymore?
It almost always comes down to one thing: cost for mass storage.
The price per gigabyte.
Exactly. SSDs are still more expensive, maybe 8 to 10 cents per gigabyte. HDDs are incredibly cheap for bulk storage, like 3 to 6 cents per gigabyte. If your client needs to store, say, petabytes of security camera footage that they rarely access, an HDD is still the most cost-effective way to do it. But for the operating system, for anything you want to be fast, it has to be an SSD.
Okay, let's clear up a huge point of confusion for new techs. M2, SATA, and NVMe. We need to be very, very clear on what's a form factor and what's a protocol.
This is non-negotiable for the exam. M2 is only a form factor. It's the physical shape, that little stick of a drive. It tells you absolutely nothing about how fast it is.
So an M.2 drive can be slow or it can be fast.
Precisely. You can buy an M.2 drive that uses the old SATA protocol. And if you do, its speed is capped at about 550 megabits per second, the same as a regular 2.5-inch SATA drive. People make this mistake all the time. They see the M.2 slot and assume it's going to be super fast.
But it might not be.
It might just be a SATA drive in a different costume.
So what's the high-performance option?
That's NVMe, non-volatile memory express. NVMe is the protocol that was designed from the ground up to unleash the speed of modern flash memory. It doesn't use the old SATA bus at all. It connects directly to the CPU through the much faster PCIe lanes.
So it bypasses the bottleneck.
It completely bypasses the SATA controller bottleneck. This is what allows modern NVMe drives to hit speeds of 3500 millips and way, way beyond. If you want speed, you need an M.2 drive that specifically says it's NVMe.
Speaking of PCIe lanes, let's talk about the thing that uses the most of them, the graphics processing unit, the GPU. We have to define the difference between dedicated and integrated graphics.
The separation here is key for troubleshooting performance. An iGPU, or integrated GPU, is built right into the CPU chip itself.
And its biggest limitation.
It doesn't have its own memory. It has to borrow a chunk of your main system RAM. It's fine for basic stuff, browsing the web, watching videos, but it hits a wall very quickly under any real graphical load.
And the solution to that is the dedicated card.
The DGPU. A dedicated GPU. It's a completely separate expansion card with its own super fast memory called VRAM. Because it has its own VRAM, it can handle massive parallel processing tasks like 3D rendering, gaming, AI calculations without stealing any resources from the CPU. This independence is why you need a DGPU for any serious graphics work or gaming.
And these cards, along with other things, plug into those PCI slots. What are some other common expansion cards a tech might see?
Well, beyond the GPU, which usually takes the top PCIe by 16 slot, you'll see high-speed network interface cards, or NICs, for multi-gigabit networking. You'll see video capture cards for streamers and content creators. And you'll see specialized controller cards, like RAID controllers for servers, or cards that just add more high-speed USB or Thunderbolt ports to a system.
All right, let's move outside the box to the peripherals.
Yeah.
Keyboard and mouse. We still have the wired versus wireless choice. What's the practical trade-off there for a technician to know?
It really boils down to absolute reliability versus convenience. Wired peripherals are still the go-to for anyone in a latency-critical role. That means competitive gamers, sure, but it also means technicians doing diagnostics.
Why is that?
Zero lag, zero chance of wireless interference, and you never have to worry about a battery dying in the middle of a critical operation. If reliability is priority number one, wired still wins.
But that wireless gap has gotten pretty small.
For most people, it has completely vanished. Modern wireless mice and keyboards are so fast you can't perceive the delay, and their big advantage, especially in an office, is multi-device connectivity.
So you can switch one keyboard between your laptop and your desktop.
And your tablet, yeah. That level of flexibility and clean desk organization is something wired just can't offer.
Now, for what might be the biggest headache in modern IT USB standards, the names are a mess, but for the A+ exam, we need a clean breakdown, differentiating the physical plug from the speed protocol.
This is absolutely critical. USB is two separate things: the connector type, which is the physical shape, and the speed standard, which is the data protocol.
Let's do the connectors first. They're easier.
You have the old rectangle USB-A, it's been around forever, and you have the new standard, USB-C. It's small, it's reversible, and it's designed to do everything. It's the only one that can handle the highest speeds and advanced power delivery.
Okay, now for the speeds, the ones we have to memorize.
This is just pure memorization, I'm afraid. USB 3.2 Gen 1 is your baseline modern speed at 5 gigabits per second. USB 3.2 Gen 2 doubles that to 10 GBps. You can find this on both A and C ports.
Then it gets weird. Gen 2 by 2.
Right. The by 2 means it uses 2 data lanes at once, so it doubles the speed again to 20 GBps. And this speed requires a USB-C connector.
And the current top speed.
USB 440, which, as the name implies, gives you a massive 40 GBps of throughput, and that also requires USB-C.
Beyond data, USB-C is also about power delivery. What's the big difference between standard USB charging and USB PD?
Standard USB gives you just a trickle of power, maybe 4.5 watts. USB power delivery, or PD, is an intelligent protocol that only works over USB-C. It allows the charger and the device to have a conversation.
What conversation?
A safe digital negotiation. They agree on the voltage and amperage needed. This allows for a variable voltage up to 20 volts and current up to 5 amps, which lets them deliver up to 100 watts of power.
Which is enough to charge a laptop.
Exactly. That intelligent negotiation is what makes it safe, and it's also why using a cheap, uncertified USB-C cable for your laptop is a really bad idea. The negotiation might try to send more power than the cable can handle.
Okay, to wrap up our look at foundational hardware, let's do a common real-world scenario. A client needs a printer. Inkjet versus laser. How does a technician advise them?
This decision is all about operational efficiency and cost. You have to start with the mechanics. An inkjet printer uses cartridges of liquid ink. It shoots tiny little droplets of this ink onto the paper. It's great at blending color, so it's fantastic for photos.
And a laser printer.
A laser printer uses a dry powder called toner. The laser draws an image on a drum, the toner sticks to that image, and then it's transferred to the paper and melted on with intense heat. That melting process is called fusing.
So given those two different mechanics, what's the clear dividing line for a recommendation?
It's all about volume and purpose. For inkjet, the pros are a low initial purchase price and superior photo quality. The con is that the ink cartridges are very expensive, so the cost per copy is high. They are best for occasional low-volume use. A home user, a student, maybe up to 5,000 pages a month max.
And laser is the opposite. Higher upfront cost, but cheaper to run.
Without a doubt, laser printers are much faster, especially for long documents, and the text is incredibly sharp. But the real win is the cost per copy. A toner cartridge can print thousands of pages, making it dramatically cheaper in the long run. They are built for high-volume environments. Any office printing hundreds of pages a week needs a laser printer. It's the only professional choice.
That feels like a good place to stop. We have built our virtual computer.
We have. We've solidified the foundational hardware concepts that are so critical for the Core 1 exam. You should now be able to see beyond just the names of the parts and understand why they matter, from how a form factor limits you, to the real-world trade-offs in new memory, to the different storage protocols.
And remember, the real value here is being able to apply this. When you're troubleshooting a slow computer, you now know to think about mechanical latency from an HDD or a mismatch between the CPU's memory controller and the RAM that's installed. You're building that system-level way of thinking.
Right. And that kind of knowledge building has to be continuous. We talked about how SSDs use wear leveling to make sure every memory block gets used equally to prevent one part from failing early. So I'll leave you with this final thought. As a future technician, what's your process? What human procedure can you adopt to make sure your own technical skills remain leveled, to make sure no one crucial area, like networking or security, wears out or falls behind the others?
That is the core of professional development right there. Keep reinforcing these concepts, keep practicing, keep studying. You're building your expertise one piece at a time.
We really encourage you to keep up the great work. Follow and subscribe to the LearnTech Podcast channel for more certification study guides. We will be here for the next block as you continue on your path to getting certified.